You know that feeling when you're sitting on a runway, you look out the window, and you just have that moment of, how in the world is this giant metal tube we're all in about to just fly? Well, today we're going to pull back the curtain and break down the modern airplane piece by piece. Okay, so let's just dive right in with this incredible moment, takeoff. It looks so powerful, so graceful, right? But what you're seeing is actually this complex dance between physics and engineering, all working together perfectly.
And that really gets us to the big question for this whole explainer. I mean, it just seems to defy logic, doesn't it? But the answer is in this amazing combination of powerful forces, really clever design, and just meticulous construction. So let's get into it.
To really get how a plane flies, we've got to start with the invisible forces that are always at play. The best way to think about it is like a constant cosmic tug of war that's happening every single second that plane is in the air.
And here they are, the four big players in this tug of war. First, you've got thrust from the engines, which is always pushing the plane forward. Fighting against that is drag, which is basically air resistance trying to pull it back. Then you have lift, generated by the wings, pushing the plane up. And its opponent? Good old weight, or gravity, which is always trying to pull it down. This table lays out that constant battle perfectly. See, for a plane to fly straight and level, lift has to be equal to weight, and thrust has to equal drag. It's balanced. But if a pilot wants to climb, they need more lift than weight. If they want to go faster, they need more thrust than drag. It's all about managing these opposing forces. Right at the very heart of this balancing act is something called the center of gravity, or CG. You can think of it as the single point where the plane's entire weight is focused, and getting its location right is absolutely critical. I mean, if the CG is too far forward, the pilot might not be able to pull the nose up to land. And if it's too far back, the plane can get super unstable and really hard to control. It's that important. Okay, so how do these invisible forces actually connect to the physical parts of a plane? They don't just exist in thin air. They act on a physical structure that's been designed specifically to control them. Now, airplanes come in all kinds of shapes and sizes, but pretty much all of them share these 5 major parts. You've got the fuselage, that's the main body, the wings, which, create the lift, the empennage, that's the fancy word for the tail section that keeps it stable, the power plant, that's your engine and propeller giving you thrust, and, of course, the landing gear for getting around on the ground. Let's just focus on the wings for a minute, because they are the real star of the show when we're talking about lift. The designs can be totally different, right? From a modern monoplane with just one set of wings to a classic biplane with 2. Each design is a trade-off. You're balancing lift, drag, and strength, all depending on what that specific plane was built to do. And a wing isn't just some solid piece of metal. No way. It's this incredibly sophisticated internal skeleton. You've got spars that run the whole length of the wing for strength, and then ribs that create that all-important curved shape for lift. This design makes the wing unbelievably strong, but also light enough to fly. It's a true marvel of engineering. So we've got the main parts, but how does a pilot actually tell the plane where to go? Well, it all comes down to these movable surfaces that let the pilot steer the aircraft through the air. An airplane moves in 3 different ways, all rotating around its center of gravity. First, you've got pitch. That's the nose moving up and down. Then there's roll, where the wings bank from side to side. And finally, you have yaw, which is the nose swinging left and right. The tail, the empennage, is basically mission control for 2 of those movements. On the horizontal part, you've got the elevator, which controls the pitch, that nose up, nose down motion. And on the vertical part, the rudder controls yaw, the nose left and right. So what about roll? For that, pilots use the ailerons, which are way out on the wings. All right, we know the parts and how to steer them, so now let's peel back the skin. How is the fuselage, the main body, actually built to be so light, but also strong enough to handle all the stress of flying? A lot of the early planes used what's called a truss structure. The easiest way to picture it is like a bridge, or even a bird cage, made from welded tubes of steel or aluminum. It's super strong for how much it weighs, but it's not very aerodynamic by itself, which is why it always has to be covered with fabric or some other lightweight skin. So, technology moved on from the truss to what's called a stressed skin design, where the outer skin itself actually carries the load. There are 2 main types. On one hand, you've got monocoque, which basically means single shell. It relies almost totally on its skin for strength. And on the other hand, and this is way more common today, is semi-monocoque. This one uses an internal frame to back up the skin, making the whole thing much tougher. This is the perfect way to think about it. A monocoque structure is just like a soda can. It's surprisingly strong, right? But the second you put a little dent in it, the whole thing can get crushed. The semi-monocoque design fixes that by adding that internal frame, which keeps that kind of catastrophic failure from happening.
Building a strong, controllable plane is one thing, but before anyone can fly in it, it has to be proven to be safe. And this is where the absolutely critical process of government certification comes in.
You see, the Federal Aviation Administration, the FAA, knows you can't have one set of rules for everything that flies. So they certify aircraft in different categories based on what they're built to do. As you can probably guess, the safety standards for a giant transport jet are going to be a little different than for a tiny two-seat acrobatic plane, or even a hot air balloon.
So once a plane meets all the required standards, it gets an airworthiness certificate. A white one, the standard certificate, is what you'll find on almost all commercial and private planes. A pink one, a special certificate, is for planes in more limited categories, like experimental aircraft or ones used for things like crop dusting. And that certificate has to be physically inside the aircraft for every single flight, no exceptions.
So there you have it. From that invisible tug of war between the forces of flight to the intricate skeletons inside the wings, all the way to that final official stamp of approval that says it's safe to fly, every single part of an airplane has a purpose. It's really an incredible testament to human ingenuity. Makes you think, though, what's the most fascinating part of it all to you?